Hello again. This is now the second movie about yaw stability of ships. And today it's specifically on the Spiral-Test-Manoeuvre for a detailed identification of the yaw stability aspect. And I will use samples of a cruise ship and also results from another ship types. And again, I will use the wonderful SAMMON Planning tool for the demonstration of the maneuvers. What can you expect today? And what will be unique? What will be important? Okay, using SAMMON is important because then you can see how to perform such a so-called spiral test. There's the name coming from this shape. This is a typical result view to show the different behavior in stable and unstable condition. This is also to highlight the different states of stability, low stable, high stable, unstable. And the final part will also to discuss how the shape of a ship, so stern form, trim of the ship, will have effect on the stability, yaw stability. Okay, so the first is, what is a spiral test? And I have here put together how you have to perform it, so the procedures. The first is steer the ship into a turning circle, maybe first with high rudder, then with lower rudder. So this is, for instance, with hard rudder turning. If you are in a steady state turning motion, it must not be a full circle. It could also be after half a turning circle. If the ship is going with a steady rate of turn, steady speed, then you should estimate rate of turn and the speed. Instead of rate of turn, you could also measure the radius of that vessel, but this is a little bit complicated, so rate of turn and speed is important. And then you have to change the rudder step by step. For instance, every 10 degrees, so here from maybe 30 degrees, here to 20 degrees, here to 10 degrees, and if you're here, then to midship, rudder midship. This ship obviously goes on a straight track when the rudder is a midship, or better to say the rudder for the neutral effect, if you know that. Then to the other side, 10 degree to the other side, 20 degree to the other side, full rudder to the other side. So this is it's one procedure of the spiral test. It's very important to repeat the maneuver from here. So if you are here in a port turning motion, then again you start the maneuver from this side and going with port 35, 25 and so forth. So you have to repeat the maneuver. If you started with starboard, then you have to repeat the maneuver starting from port side. And the most important phase is then if you are close to rudder midship position. For some ship, it's maybe even helpful not to go from 10 to midship, maybe 10 to 5 to 2, 1 degree midship, 1 degree to the other side, and so forth. The results of all these experiments goes into a characteristic diagram. And this spiral test was for the AIDA Blue model. And I have here the results. And the diagram has on this axis, as a standard, so to say, the rudder angle from 0, 20 up to 40 degree maybe for this ship. And here on this axis, there's the rate of turn. This is most important. Maybe if you have measured the speed, then also here's a scale for the speed measuring. And I made this test even for 2 engine orders, so 2 speed rates with 73 degrees. In this case, the ship was cruising with about 18 knots, and also with a engine order telegraph 30 degrees. In this case, the ship was running with about 6 knots. First, with a high speed. So these are the results. For instance, the rate of turn for 40 degrees, it's about 50 degrees per minute, and the speed was, in this case, 5 to 6 knots, for instance. Then the rudder went to 30 degrees, to 20 degrees, 10 degrees midship. So the ship was going straight. That's we have seen in our experiments before, and then to the port side and so forth. And for this ship, it's characteristic that if you start the maneuver then from here, from 40 degrees, and you go back, then you get the same results as you had starting from here. So both results from both sides are the same. You might ask why I have done this in 2 speed rates. So this is, for instance, the speed distribution for only 30% engine order. And these are the lower rate of turn for the same rudder angles. You got a lower rate of turn with ship because the ship is running slower with slower speed. And I have told it already when we talked about turning circle dynamics that the turning circle diameter is independent from the speed rate. I made it also here, so I used the data for rate of turn and for speed in this small equation. The rate of turn is the ship speed divided by the radius, as you see it here. And so we got the radius here out of this data. And you see, for both experiments, for both speed rates, we got the same, nearly the same radius. So the radius is not depending on the speed. Therefore, sometimes in ship design or ship theory, you better use on this axis the radius, maybe also non-dimensional for the spiral test. But for ship operators, it's better to use the rate of turn because you can read it immediately. Okay, so the next ship is the Costa Fortuna. These are already the results, but I will show the most important thing if you go to regions where the rudder angle is very small. So we have here the Costa Fortuna running in a turning circle, and I already moved the ship up to this position. So after one circle, we are here. So normally we would, in our place, we would measure the rate of turn and the speed here, and then we would change the rudder. So I add a maneuvering point to change the rudder. Maybe now we will make it a little bit faster. This is 20 degrees. So I move the ship to the next position. So I move the ship up to here. Then I add a maneuvering point. I go to 10 degrees, 15. I go to 10 degrees. Then I move the ship again up to here. And then I add a maneuvering point and I move the ship to midships. So what you see here, the ship is not coming to a straight motion. It's going still on the turning circle. I enlarge the picture a little bit to enlarge the display. So what we see is for midship rudder, this ship is not going straight as we have seen for the Costa, for the AIDA Blue. And for midship rudder, we have a rate of turn of about 25 degrees per minute. We know this ship is unstable. That's what we have seen in our experiments in the previous movie. So from here, you would go now to other turning. I will enlarge the picture a little bit. to allow the full picture. So from here we would then go to 5 or 10 degree to the other side. So we would go here with the ship to this position and continue our spiral test with 20 degree of rudder and so forth, ending up then in the spiral. But to show the results in a diagram, we will go back now. So here we are again. What we see is if we have moved the rudder from 30 degrees, 20, 10 degrees, even to smaller degrees, and then to midship, then we see coming from this side, it remains a turning to starboard. And then with the next, it jumps to port turning and so forth. But if you repeat the maneuver from port side, then you will get for midships rudder a turning to port side remaining. So this is the typical behavior for zero rudder. That means for this rudder angles, there are two options possible: to port or to starboard. The ship is obviously unstable, at least for the small rudder angle range. In this case, only between plus minus 1 degree. So the range of instability is very small. This is explained as this typical diagram as a result for spiral tests. So I have shown here two different results for a stable ship and for an unstable ship. You even can speculate in what direction it's going, because this is normally for stern trim and this is for bow trim. With a huge bow trim, you can make even every ship unstable. And what you see also is these graphs, these curves, are a little bit shifted to the port side. This is happening if we have, for instance, a single screw vessel and you have a certain rudder angle of neutral effect. Maybe there's a paddle wheel effect of the propeller, and so you need maybe 1, 2, 3 degree to one side to keep the ship straight. Therefore, it's a little bit shifted. But it's important that we have, for the unstable vessel, we have a range of instability. This is exactly for these rudder angles. This is a so-called spiral loop width. So maybe it's from plus to minus 10 degree. And this means in this range of rudder angles, you have always 3 results of potential ship motion, equilibrium conditions. Within this range here, the broken line here, this is highlighting the unstable range or unstable conditions. Maybe for rudder angle 0, there might be possible, again, a very small turning rate to one side, which is an unstable condition. So the ship would always try to get away from this. And 2 stable conditions, 1 to port and 1 to starboard turning. So, and this marks the range, the spiral loop height, where we have unstable conditions. What I should say is it's important that this broken line here, these conditions are hard to measure in a trial, for instance. You would say, or you would try to stabilize the ship around maybe midships. That's what you're doing in your course keeping activities. So it's not possible to get this broken line by a regular spiral test. It should be a reversed spiral test, where you say, I want to get rate of turn of 0, and then you have to steer the ship with the rudder, and then the average rudder angle would be taken. But this goes too far. What is important is the slope of this curve. The slope of this curve says something about the stability. So for this graph, it's always a positive slope. I mentioned that already in the wind stability movie. So this is always positive slope, and in this range the ship is stable. In this range the slope is negative. In this range the ship is unstable. So the slope is saying something about the stability. But I will come back to these different states of the stability. I have, put together several grades of stability. So the green one is a normal stable ship, according to this, or what we have seen for the AIDA Blue. The marginal stable, this is close to the Costa Fortuna. So in the range of low rudder angles, small rudder angles, there it's unstable. We call it marginal stable. And these are high unstable vessels. So you need even rudder angles to the other side to get out of one turning motion to the other. You need always bigger rudder angles to the other side. But the opposite is highly stable vessels. This is strange because what you see here is maybe if this 10 degree starboard, 10 degree port side, then it would mean for all of these rudder angles between plus and minus 10 degree of rudder angles, the ship is always going straight. So it's nearly no rudder effect. This is very stable. So you can even put a little rudder angle and nothing happens. This is highly stable ships. What I want to show here is the effects of trim. The effect of trim. And here you see two results from a tanker, the tanker Patriot. The upper one is in ballast conditions with trim to stern. So you see the result is nearly a straight line for the rate of turn. If you use this rudder or this, it always increases the turning rate by a fixed linear ratio. And this is the same vessel, but in bow trim. This means you see here clearly that we get a range of instability of about 7 degree. That is the spiral loop width, and with the same rudder angle, so the rudder angle of neutral effect is here about 4 degrees because of the pedal wheel effect of the propeller. But for these 4 degrees, you can get minus 20 or plus 20 degrees per minute turning rate. So this is the effect of trim, because the unstable forces and moments at the bow are much bigger than the damping forces at the stern. And now some other aspects are important for the yawing stability. For instance, the L to B ratio, length to beam ratio. A long ship, a container, it has long levers of stability and damping forces. So this ship is more stable than a ship with a shorter length, like a tug. So this is close to instability or really unstable. High block coefficients, so if you have voluminous bodies like tankers or bulkers, like a rectangular shape, like a block, like a box, this will decrease stability, so it's less stable. And then there's the effect of appendages. For instance, skags, flaps, or fins, that's the rudder, for instance. And in general, big rudders, they have a stabilizing effect. They will increase the stability. For instance, for potted ships, when they came out, they had in the beginning, they had this U-shape stern form, which is not good in damping at all. And so these ships were very unstable. And so they have used additional means like skags. You see here some skags. So to add a skag in the middle, in the center between both pods, only as like a fin, so to say, stabilizing fin to keep the ship straight. Or you even have to add another fin area or skag area to get the ship stable. This might come to the question, is it good? Is stability, yaw stability, is it good or bad? Is it better to have high stability or low stability? There's an interrelation between turning ability and yaw stability. If the yaw stability is low, like for a tug for instance, there's an improvement of turning ability. So the turning circles are getting smaller. You see here, for the same rudder, the ship in bow trim, the unstable ship, has a higher rate of turn, so it means a smaller turning circle than the ship in ballast condition. And if the yaw stability is high, then there's an increase of course keeping. So you have to look for a compromise. As a ship designer, you have to look for a compromise. If you want to have very good turning ability, the ship could be unstable. But if you want to have a ship which is going for days or weeks straight, then it's better to have a ship which is stable. The final part is here the effects of instability on the maneuvering behavior. So what effect has it? Instability decreases the vessel's safety, or might decrease, because there could be unexpected turning when you don't want to do it. Or if you have to steer the ship over the Atlantic and the ship is unstable, it might even happen that your autopilot is out of order because this strange device does not know that to get out of a starboard turning, you might need a very big rudder angle to the other side. This effect leads to an increase of fuel consumptions. If you get always big off-track errors, and I have made an experiment with the tanker I already have shown before, and this is for a zigzag test. So this is like a course keeping test, where you use the rudder, here in this case 10 degree to port side and to starboard side periodically to keep the ship in a certain direction. And you see here, the red one is for the ballast condition, the tanker in ballast condition. You see with these 10 degree rudder angle from one to the other side, the ship goes nearly straight. The track offset is not that big. But for the unstable vessel, with the same rudder activities, you got such a big swing, overswing angles of about 60 degrees, so it's hard to keep that ship along a certain track for course keeping. And so you also get higher fuel consumption. Okay, with that, I like to stop this video, and so you might wait for other videos to come, because there are more tests than the spiral test. And I will tell the difference between all these tests and the results you can get with this test. Thank you very much.